What are we gonna do today? Today you're gonna learn about covalent bonding, okay? Covalent bonding, because remember that a month ago we were covering ionic. You already learned about ionic bonding, and you already know how to name ionic compounds in which the acids are included. Review, just to refresh, that sometimes you're having problem with your short memory. This is just to review. Okay, what do the atoms they bond? Okay, they bond because they have to gain chemical stability. See, it's not because they want to, no, but because they feel like it. No, they are bonding because they need to reach chemical stability. How are they going to reach that chemical stability? By having A electrons, the octet rule. Remember that? A electrons on the last level of energy with only one section, hydrogen. Hydrogen is the smallest element on the periodic table, so hydrogen is going to be happy with only 2 because he has only one level of energy. And remember, 2n to the second power in the first level of energy, elements, they are able to accommodate up to 2 electrons. Okay, so the only one that is going to be happy with 2, hydrogen and helium. But helium is a noble gas already completed. He doesn't need more. Wow, Miss Ramos, what is this? Okay, just a review. We're going to start with ionic, okay? Bonding, okay, when electrons are gained are lost by metals, or when they are shared, okay? So in an ionic bonding, you have a metal combined with a non-metal, okay? The metal, let me put it over here, is forming the cation, which is the positive ion, while the non-metal is forming the anion, which is the negative one. Okay, the metal is losing electron, and who's gaining those electrons? The non-metal. Okay, and remember that at the beginning of this topic we were talking about electronegativity. You're gonna have an ionic bonding when the difference in electronegativity is bigger than 1.7. A genuity was putting over there 2, which is what is expected, because when you look at the periodic table, electronegativity is gonna increase from left all the way to right. So the difference in electronegativity between a metal and a non-metal always is gonna be bigger than 1.7. See, that's not new. When you see a metal combined with a non-metal, always the electronegativity, the difference in the electronegativity is going to be bigger than 1.7. The other type of bonding, covalent. What's happening in covalent bonding? In covalent bonding, let me get mine. You have 2 non-metals that are sharing electrons. Why, Miramos? Why no one is gaining and no one is accepting? No one is gaining or accepting because the difference in electronegativity is too small. So it's going to be smaller than 1.7. Okay? See, none of the atom is strong enough just to gain the electrons. Okay? Now, what happened? Okay, we have 2 types of covalent bonding. We have the polar one. This is important, super important. Polar one, when the difference in electronegativity is between 0.4 and 1.7, you have a polar covalent bond. Okay? Because the electrons, they are shared unequally. See, meaning that one of the atoms, usually the one with more electronegativity, we usually know it's always the one that is more electronegative, is gonna be pulling the electrons with more force, and consequently, okay, the elements that are involved in that polar covalent bonding, they are gonna become partially positive charge or partially negative charge. If that's the case of water. Yeah, I don't know you're understanding this. I'm going to repeat one more time. When you have 2 non-metals, and when you look at the electronegativity of those 2 non-metals, the different electronegativity is between 0.4 and 1, or smaller than 1.7. The bonding is covalent polar. See, covalent name, polar last name. Why? Because the elements, they are not sharing the electrons equally. One of the elements is attracting the electron with more force. Because of that, you're going to have partially charged, okay, part of molecules in there, because you have to keep in mind that when elements, they share electrons, they don't form formula units like the ionic compounds. They are forming molecules. Okay, now when that difference in electronegativity is smaller than 0.4, you have a covalent bond that is not polar. Covalent the name, non-polar the last name, because they are sharing the electrons equally, same force. Okay, so you don't have partial charged particles in there. Questions about that? No questions. No questions in the chat. Okay. And I'm going to start with single bonding. In single bonding, only one pair of electron is shared. Single bonding, they are also known as sigma bonds. Okay? And that's the Greek letter that is representing a sigma bond. And I'm going to show you a sample of a single bonding by drawing the Lewis structure of this covalent compound. See? That's the chemical formula. CH4. That's methane, an organic compound. See, you have any compound that is made of carbon and hydrogen. Carbon, hydrogen, or oxygen, those are organic compounds, and we follow different rules to name them. Okay? So, as you can see over here, you have two non-metals. You have a covalent bond between the two elements that you have in there. Okay? So, a single bond between the carbon atom and the hydrogen one. And I'm going to show you that over here, see? Because one of the class objectives today is that you learn how to write the Lewis structure for covalent compounds. How are you going to do that? How are you going to do that? First, you're going to start. See, remember in ionic compounds that you were drawing first the electron dot diagram. You're going to do the same with only one difference. Okay, remember the oxidation number was giving you the amount of atoms that were involved. Here in covalent compounds, I'm going to give you the formula. Okay, I'm going to give you the formula. So you have over here, if you look at the formula, you have one atom of carbon with 4 atoms of hydrogen involved. Okay, when you are drawing or when you're trying to draw the Lewis structure for a covalent compound, you're going to start with the electron dot diagram. If you know that in the electron dot diagram, you are representing the valence electron. And what is the definition of valence electrons? Electrons that are ready for bonding. Okay, you're going to represent the valence electron using dots in there. And that's what I did over here. Okay, so as you can see, you don't have pair of electrons. The 4 electrons around carbon, they're ready for bonding. And the only one that hydrogen has in the first level of energy is ready for bonding, because you don't have a pair of electrons in there. That's the first step, just to draw the Lewis structure for the elements that are involved in the compound. The second step, okay, you have to analyze and you have to ask yourself, what is the atom with less electronegativity? Because that's the one that goes in the center or you're drawing. Now, hydrogen is an exception, because if you look at the electronegativity values between carbon and hydrogen, carbon is the atom with less electronegativity, but hydrogen is an exception. Okay, the only exception, hydrogen. Even though hydrogen is the one with less electronegativity, that's not the one that you're going to put in the center. So every time that you see carbon bonded to hydrogen, the carbon goes in the center. Is that clear? Okay, whatever. I'm going to continue. So, but when you have other elements involved in your covalent bonding, the one with less electronegativity is the one that goes in the center. And I'm going to show another example in here. So carbon in the center, see? And then you're going to draw, I did that, the 4 dots in there. Now you're going to look at the formula. How many atoms of hydrogen are involved? 4. And I'm going to draw that around my carbon atoms. See that? Now, my third step, I have to replace the shared electrons. Okay, by the way, I have to put over here. Okay. I have to replace, see that? The shared electrons are going to be sharing that pair. They're going to be sharing that pair, sharing that pair, and sharing the pair. So my third step when I'm drawing the Lewis structure is just to replace the pair of shared electrons with lines. And that's what I did over here. See that? That's the Lewis structure for methane. Lewis structure for methane. And as you can see, since carbon is sharing one pair of electron with every hydrogen atom, I have over here a single bond or a sigma bond. And when do you have a sigma bond? When s orbitals are sharing the electron with another s orbital or a p orbital. Okay? That's a sigma or a single bond. Now, are you done? Yes, you're done, but you have to make sure that everyone is happy. So you're going to count. And that's what I did on the next step. Okay? Remember, in order to be happy, they have to fulfill the octet rule. So I have 1, 2, 3, 4, 5, 6, 7, 8. Carbon is happy. 1, 2. See, I have 1, 2 for every hydrogen atom. And you know that hydrogen is happy with only 2. So I'm done with this. Questions about that? And this is a molecule. Molecule. Okay, I'm going to continue with example number 2. Continue with example number 2. See? Always I'm going to give you the chemical formula. Okay, by the way, I don't know if you have noticed, but later you will learn about that. Nitrogen trichloride. How do you name covalent compounds? You use prefixes. If the prefixes is telling you the number of atoms that are involved, but we're going to do that later. Okay. Now, nitrogen, I want, see, just to draw the Lewis structure for that covalent compound. And I know that it's covalent because I have a nonmetal and a nonmetal. For one atom of nitrogen, how many atoms of chlorine do I have in there? 3. So my first step, electron dot diagram. And look at this. See that? That pair of electrons is not available for bonding. It's not. No. In the s orbital, you have the pair one that is spinning right, the other one is spinning left. They're not ready for bonding. And over here, in chlorine, you have only one that is ready for bonding because the other one are in pairs. Questions about that? No? Now, you have to analyze nitrogen and chlorine, which one has the smallest electronegativity. If from left to right is increasing, you need a periodic table. Nitrogen is in group 15, while chlorine is in group 17. Which one is more to the left? Nitrogen. That's the one that I'm going to put in the center. That's what I did over here. Over here. With all the valence electrons. So I'm going to look at the formula. I need 3 chlorines, and I'm going to do the same. All the valence electrons. Next step, just to look for pairs that can be shared. That pair over there is not ready to share. And when you have all the valence electrons, you're going to look for pairs that can be shared. And that's what I did over here. The third step is just to replace the pairs that are shared with a line. And that's what I did over here. Only one pair of electron has been shared, so you have a single or sigma bond. Questions about that? No? This is the Lewis structure. Mirama, what's gonna happen if I don't put all the dots around? That's wrong. What is gonna happen if I don't put that over there? That's wrong. And then you can count. Remember, you need to fulfill the after rule. 1, this is for nitrogen. 1, 2, let me see. 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen is happy. Now I'm gonna do the same for chlorine. 1, 2, 3, 4, 5, 6, 7, 8. Because the line is representing a pair of electrons that has been shared. Questions about that? And this is the Lewis structure for the nitrogen 3 or trichloride molecule. Questions about that? On the test, I'm going to put all of this. See, you're going to have time to calm down during the test. I'm going to give you the formula. You have to draw all of that, step by step. Questions? No? Okay. Mis Ramos, what is this? Okay, simple. I'm explaining the same using the definition that you have in a genuity. Because according to a genuity, single bonding or a sigma bond is going to take place when you have two s orbitals that overlaps with an s or a p orbital, or two p orbitals that overlap ends to end. I'm not going to explain this, because if you don't know electron configuration by now, you are in trouble. You will learn that in college. Don't worry about that. Don't worry. We are not planning to teach AP chemistry in this school, so you don't have to worry about that. If you don't know that, that's your problem. Okay? Or you don't have to worry about that, because you will learn that in college. In college, you're going to learn that one more time. You're going to learn this, a molecular shape. So you don't have to worry about that. Just if you want to take a look at that, you will see how the sigma bond is made, because S is sharing, see, an s orbital is sharing electron with another s or a p, or because you have two p orbitals that are overlapping end to end. I'm like explaining all of that in here. Okay, so if you want to look at that later, that's up to you. Covalent bond, it could be single, like the sigma. It could be double, like the one that you have over here. When you have double or triple bonding of the same element, you have a diatomic molecule. If you were in my physical science class, you already know about diatomic molecules. Diatomic molecules are molecules made of two atoms of the same element. Two atoms of the same elements. Two atoms of the same. See, I'm repeating that. What are the elements that have a high tendency to form diatomic molecules? You have examples in there. Hydrogen, nitrogen, oxygen, and all the halogens. You remember that when you were learning about the periodic table, we were discussing the chemical property of halogen. They are so reactive that they're going to react with themselves, forming diatomic molecules. What are diatomic? One more time. See how many times I'm saying this? Diatomic molecules are molecules that are formed after two atoms of the same element are sharing electrons. Questions about that? No. Okay, you have an example in there. An example in there. See, it does, okay. Over here, I'm showing you the Lewis structure for the diatomic molecule for oxygen. Okay, see, you can see the two lines over there is representing the double bonding. Okay, Ms. Ramos, now double bonding, which one is a sigma one? You know that a sigma one is when the s orbitals are shared, see, are sharing electron with another s orbital with a p, or when the p overlaps. Yeah, I'm explaining that over here, in case that you are interested. Okay, explaining that over here. The overlapping of the s orbital and the overlapping of the p, or the p orbitals. So when you have overlapping of the s, you have your sigma bond, overlapping of, see, when you have parallel p orbitals sharing electrons, then you have a pi 1. Do you have to know all of this? No. The only thing that you need to know is that when you have a double bond, One is going to be sigma, the other one is going to be pi. Questions about that? Now, why is oxygen doing this? Why is hydrogen doing this? Why is nitrogen doing this? Or the halogens? Why do they form? Okay, by the way, remember that the halogens, they are located in group 1. Okay? I know. The halogens, they are located in group 17. Okay? They have 7 valence electrons. So they're going to be sharing only 1 pair of electrons. Or the halogens, they are formed diatomic molecules by sharing 1 pair of electrons. Questions about that? No? Okay. Now, why are they doing that? Why are they sharing 1 or more than 1 pair of electrons? Because they are more stable. When they form a diatomic molecule, they are more stable. Okay, you know that oxygen is reacting. Oxygen is a non-metal that is reacting with all metals. But I'm sitting here in a class and the frames of the doors, they are made of aluminum. Aluminum, which is a metal. And we have the air over here in which, see, 71% of that air is oxygen. Do you see the aluminum reacting with the oxygen that we have in the air? Why not? Because oxygen is in the form of a diatomic molecule, so it's stable. The cover, no. See, bueno, it's the covering, see, the finish of the faucets that we have here in the sink, they are made of nickel. Do you see the oxygen in the air reacting with the nickel? No. It's because of this. Because oxygen is able to share 2 pairs of electrons with another oxygen atom to become more stable. Questions about that? No questions about that. Okay. So, Ms. Ramos, does that mean that when you have a double bond, only you're going to have diatomic molecules? No, you're going to have covalent compounds. Compounds, because the diatomic molecules, they are not compounds. No, that's an element. Element that was reaching stability by sharing 2 pairs of electrons. Okay, in that case, remember that the halogens, they're going to be sharing only 1 pair of electrons. No, okay. Not only diatomic molecules, they share electrons. Compounds, they're going to be sharing 1, 2, or 3 pair of electrons too. Regular compounds. So one example that you have over here is carbon dioxide. That's carbon dioxide. How many atoms of carbon do you have there? Only 1. How many atoms of oxygen? You have 2. So let's say that you want to draw the Lewis structure for that compound. See, it's a covalent compound. You don't have a cation, you don't have an anion. Okay, so you have 1 atom of carbon, 2 of oxygen. You're going to start with the electron dot diagram, which is over here, electron dot diagram. Your first step, which one has less electronegativity? Carbon is in group 14, oxygen is in group 16. As you go from left to right, electronegativity is increasing. So carbon is the one with the smallest electronegativity. And I'm putting that on the center because it's the one with the less. Remember, the hydrogen is the only section. Okay, less electronegativity. 1, 2, 3, 4, valence electrons. So all of them, they're ready for bonding. But look at the oxygen. These 2 over here, they're not ready for bonding. These 2 over here, they're not ready for bonding. What are the only ones ready for bonding? 1 and 2. Okay, so you're going to draw lines for electrons that can be shared. Start with a single bond and then you continue with double bond. See that? So they are sharing 2 pairs of electrons. Carbon is sharing 2 pairs of electrons with every oxygen atom. And this is my Lewis structure over here. Lewis structure for carbon dioxide. For carbon dioxide. Now, the polarity of the molecule also depends on the shape of the molecule. Do you see? See, when you have that over here, when you have 2 electrons that are not ready for bonding, we call those 2 electrons lone pairs. Lone, but you don't need to know that now. Lone pairs. And those lone pairs, they are exerting a force in the other atoms. So do you have any lone pairs in here? No. That's important for the polarity of the molecule. But you will learn about that in college because we're not planning to teach AP chemistry. Okay? Questions until now. I'm going to stop over here because today is Friday. I'm going to stop over here. Next class, I'm going to continue with triple bonding and more of the Lewis structure and naming. Questions about this? No? You don't have any questions about this? With this information,